In section 10.6, we start to expand a little farther than the Lewis dot structure model of molecule and covalent bond interaction. We start talking about the first of the advanced theories, which is valence bond theory. And this is where we're looking at orbital overlap as a chemical bond in a little bit more detail. So with valence bond theory, it's the simpler of these two additional models we're going to talk about in this chapter. Electrons are in hybridized and unhybridized orbitals. So the ones like S, P, D, F that we have talked about previously are the unhybridized orbitals, while the hybridized orbitals are the S, P2, SP, SP3, etc. type orbitals that you may have read about already in the book. It's a pretty straightforward idea in terms of a bond is formed when the overlap between the two orbitals of the two nuclei, and the nuclei are shown here in pictogram style as the little black dots in the center of the blue electron density cloud, and when they approach each other, the two nuclei approach each other and their orbitals overlap, we have a certain amount of energy. And that energy in that molecule decreases as they get to a certain distance apart. And that distance corresponds with the opportune or the precisely perfect position for the electron overlap cloud to be in order to hold those two molecules, those two atoms securely together. So by having a minimum amount of energy, that results in a stable molecule. So remember, lower energy is conducive to molecule stability, and we can kind of think of why that would be just by thinking about something with a lot of energy has the ability to react, has the ability to change, has the ability to switch its bonds with something else. So stable means you stay in your current compound state or current molecular configuration without changing. So low energy, stable molecule. If we get the atoms too close to each other, the nuclei start pushing on each other, and all of a sudden we built up a whole bunch of energy, like pushing the two wrong sides of a magnet together while they're trying to push each other apart. As we get farther and farther away from the atoms, eventually we get back to zero energy again, where we have no real attractive force and we have no real pushing force. Basically, the two atoms aren't associated with each other anymore. So bond length is the position where we have the minimum energy for the whole molecule as one piece. Now, to do that with molecular overlap, we can kind of look at H2S as an example where no hybridization occurs, and we can pair up electrons in orbitals between the sulfur atom and the hydrogen atoms in H2S, and we can think of a bond forming between this 1s orbital and the open space in one of the 3p orbitals of the sulfur. So sulfur with its valence state is 6. It has 6 electrons. So one hydrogen combines with 3p orbital with its 1s orbital, and a second hydrogen will combine its 1s orbital with the sulfur's 3p orbital. And when that happens, we have a filled p orbital, a p orbital that is overlapping with a hydrogen right here. So sulfur's 3p bonds with hydrogen's 1s, each of them contributing 1 electron, and the second hydrogen is also doing the same thing. It's using a different 3p and a different hydrogen's 1s, but these are in p orbitals on the sulfur. Well, the bond that would form from that would be about 90 degrees, and as opposed to the hybridized models that we've been looking at a lot more when we talk about shape, these ones are unhybridized and actually are about 90 degrees. If we measure it, we'll find it's about 92 degrees between the two hydrogens. So H2S is actually an example where hybridization does not occur, and the orbital overlap and sharing with the electrons between the two orbitals occurs in unhybridized s and p orbitals. In the next section, we'll look at how this theory can work with hybridization occurring.